For our next problem, uh, uh, hopefully we can get past what is probably going to be a not one of my best drawings, but let's see where we can go here. So I have a tabletop disc, all right, and that's on a base and it's rotating. So this whole disc is rotating at 5 radians per second z. So this would be counterclockwise as we look down. And that's the speed, notice is at start. So initially, this disk is rotating at 5 radians per second. Okay. The base where it's rotating is frictionless. And on this disk here, we have 2 supports and a frictionless rod. All right. And on that rod, there sits a cylinder. Cylinder A. Took this out of a text, so this was called cylinder A. And initially, that cylinder is in the center of this rod, which would be over the center of the table. Now, if it was perfectly at the center of the table, and there was nothing to motivate it to move, it would just sit there and spin while the table spins. Okay? But if it was just slightly perturbed off of the center, or given the slightest bit of a nudge, that would drive it. So let's say it was nudged a little over this way. That would drive this thing out to this point B here. All right. And so as this spun, that would just boom. It would just shoom, drive out. So the cylinder, the length of the cylinder is 0.3 meters. We see that right there. And initially, the cylinder again is centered relative to the disc and this rod. So if we look at the problem statement, it says cylinder A is free to slide, frictionless rod, okay, which is attached to the 50 kilogram disc. That's what this is, which is initially at 5 radians per second. The cylinder is initially at x equals 0, or I should say d equals 0, and given a slight push to motivate things to start to move. And so then what the problem is, determine the angular velocity of this disk when the cylinder strikes B. And that'll happen when x equals, notice here, relative to the rod, z comes out of the center of the disk. Okay, x goes here, y is perpendicular to the rod at the moment. There. Okay? So find omega disk when B strikes at x equals minus 0.6 meters. We'll neglect the mass of the brackets and the smooth rod, so they will not have any effect on angular momentum. So if we look at what's going on here, we're being asked for velocities, and it's tempted to say that this is, we have velocity, omega, and we have distance. But you will notice that omega would be looking, its equivalent displacement would be theta. This is a translation. If you were to try to do this with energy, it's asking for omega after it's gone through a distance. If you try to do this with energy, you will hit a wall. Let's talk about what that wall is. So you have this here. So let's ignore the first statement here. If we used energy, all right, there's no external, there's no friction, no motors, no springs, and everything stays at the same height. So what you have is initial kinetic energy equals the final kinetic energy. All right. So we have this disk because we're treating everything else other than this cylinder and this disk, everything else is massless. So kinetic energy would be 1/2 I omega squared relative to the center of mass. So this is, I'll just note that for the disk, the mass moment of inertia is 20.25. So initial kinetic energy is 1/2 I omega. We were told at first it's going at 5 radians per second. The cylinder will be in the center, so it would just be spinning. So, and its mass moment of inertia is 0.2625. So 1/2 I omega squared. Now, once this thing gets a little off center and then goes flying out to the end, what happens? What would be, the question was, what is omega? Fine question. So you'd have 1/2 I, now this is omega squared because we don't know how fast it's going. But let's look at this cylinder, okay? Its velocity has two components. Okay, if you were to look at Vg in here, okay, because of the rotation, Vg has a velocity in this direction, and it's sliding out. So just before it has impact, it has an axial direction of velocity. All right, so we've got two components here that we have to consider. So we have 1/2 I omega squared. So, because this is spinning, so we have that, and then we have to look at 1/2 mv squared, because Vg has a velocity this way and a velocity along the axis. So here's the 1/2 I omega, because this is rotating. Oops, I should let you see the pen as it goes around. Okay. And then we have the 1/2 m. Oops, bring it over. 1/2 mv squared. So 1/2 20. As this goes out 0.6 off the center, 0.6 meters. So 0.6 times whatever omega is the velocity perpendicular to the rod. And then we have 1/2 mass times whatever the velocity is along the axis of the rod. So this thing here is a velocity, 0.6 w is a velocity in the y direction, so that's y squared, and axial is x squared. We know nothing to figure that out. This is our problem. So if you try to use energy, you're going to get in trouble here. Okay? Now note that they said this was a frictionless rod. All right? If it wasn't frictionless, then we would have in here a non-conservative friction term that would be slowing the system down and would obviously affect the answers that you get. So that's why it's important that this is frictionless from an energy point of view. So here's the thing. We need to actually use momentum. That'll allow us to get omega. Then we could come back and use energy to get this. We'd know everything else, and we could solve for that axial component. So this is you normally when you see velocity and distance, you immediately go after energy. But there's exceptions to most every rule, and this is one of them. Okay? So let's see, we're going to use momentum to do this and contemplate how to go about it. All right, so we note here that it says D measures distance off of the Z along the x-axis of the cylinder center along this rod. And we have here other dimensions. The cylinder radius is 0.15. Here's the length, 0.3. All right, so let's, if we look at what's happening here, everything's just rotating and there's no outside forces, no outside moments. Okay, so in a sense, this is kind of like the ice skater that has their you have they adjust their mass moment of inertia, and as they bring their arms in, I changes, and so omega changes. So we have conservation of momentum. The initial angular momentum equals the final angular momentum. All right, so this is really a red herring to this. All right, so we have no external angular impulse. So we're going to, relative to the z-axis, there's no external angular impulse. So let's apply angular momentum on the z-axis. That's how this thing is rotating. Let's see what we get. All right, so we already used these just a little bit earlier, but cylinder A, here's the equation for mass moment of inertia about the centroid. comes out to, here's the equation, apply the numbers, 0.2625. I had mentioned that earlier. The disk is simply 1/2 mr squared, works out to 20.25. We use that in that page we just showed. All right, so we have conservation of momentum because there is no external angular impulse. Okay, so for state 1, the cylinder is in the center, okay, where the velocity of the center of mass of this, picture the center of mass of this cylinder is right on the center here, okay, so its velocity then would be 0. So let's start constructing this. So we have H1 would consist of Ig for each of these, of the cylinder and the disk, times omega. All right. The disk can only rotate. The cylinder, as it comes off of the center, will be both translating and rotating. All right, so that's just our initial situation, the initial state. What's state 2? Okay, so for the state 2, relative to the disk, 20.25 times omega, which we want to compute. All right. What about the cylinder? All right. So the cylinder will have it's still, because this thing is rotating, so it still has a rotational component, so I times omega, but it also has a translating component. So what do? Since we're not here in the center, we have an R from the center to the center of mass, and that'll be minus 0.6 meters cross mass times the velocity. And notice here we have a velocity along the x, so I have v cylinder axial, and technically that'll be negative velocity, minus 0.6 omega. So it's 0.6 meters out times omega would give a velocity which would be going this way. Okay, it'll be in the negative y direction. All right, but here's the thing. Because we're doing r cross velocity, the r is in the x. So this cylindrical axial velocity gets wiped out here. In energy, it wasn't wiped out, and so that was going to cause us trouble. Here, we get rid of that term, so we are just left with an x cross y, no problem. So here is h1 equals h2. We have our only unknowns are omegas. So we simply crunch that out, and then we can solve, and we get 3.7 radians per second z. So it's actually slowed down a little bit. Back in a few.